So now we're going to talk about the populations of the two different states. So the number of, let's start with this one. The number of, so number n of nuclei with spins in this lower energy state are proportional to the rate of absorption. Okay, so when you have a photon coming in the radio frequency, this is going to absorb that energy, if and only if you've got an occupation that it can actually flip into that other particular state. This, however, can't flip out of its state and go back into A, or alpha state, unless it has stimulated emission. So the incident photon is going to cause this state here to, let's say that this one has jumped up, as in it's flipped its spin. Now this can't flip its spin unless there's a state that's open down here. And so there's going to be an inversion that's happening. So this, the number in the beta state is proportional to the rate of stimulated emission, and the number in the alpha state is proportional to the rate of absorption. So there's your resonance. You've got two states having to work in tandem. Absorption techniques, it's a free-for-all. Electrons like, yep, cool, take that energy and I'll jump up because it's got almost infinite numbers of states to go into. Not always the case. And so you have to have a resonance between the two states. Okay. So the rate and the rate of actual the rate of having the resonance condition, the rate of is proportional to, actually I'm going to make this very proportional to the difference between N alpha minus N beta. So only if you have those states to occupy, as in you have a slight difference between these two, difference between the two numbers occupying the alpha and the beta state, will you have your resonance condition met, under the condition that you've got the right frequency for the spacing. So the intensity of the absorption is proportional to N alpha minus N beta multiplied by B0. Okay, and this is the applied magnetic field. All right, everyone good? Cool. So now I want to know, what's the population difference? And so from Boltzmann statistics, I know that N beta is proportional to some number of, so basically the frequency factor E to the minus E over KT, where this is your energy state. And so then what you can get is N beta over N alphas. Okay, so we're using Boltzmann statistics. I won't go over this because this is what you will learn in thermodynamics. Or if you just had thermodynamics with me, you're like, hey, I recognize that. But we want to know, what's the population of beta out of the total that are available that can jump up into or can exchange into this higher state? Well, that means we want to know the population of N beta to N alpha. This is also going to come in handy. So using this relationship of Boltzmann statistics, we can then say that this, that's me not going into it, is equal to E to the minus delta E over KT. So what we can do is now look at the difference in the energy states, which is good because that's exactly what we want, is related now to the population difference. But this is approximately equal to 1 minus delta E over Boltzmann times temperature, that thermal energy KT, if delta E is much, much smaller than KT. Okay, and these are little B's, by the way, to designate the Boltzmann constant. I should designate that Boltzmann constant. Okay. So using a Taylor series expansion, we can look at this population difference. E to the minus delta E over KT is approximately equal to 1 minus delta E over KT if the change in this energy state is very, very, very small compared to the thermal energy that's in the room, in the system. Okay, KT is a very important quantity. It represents, so if you have something that's like, I don't know, 20 degrees Celsius, how much energy is that? Well, you take your 20 degrees Celsius, you multiply it by your Boltzmann constant, and that's where you get the energy that's contained within that temperature. which again, if you think about it, it's kinetic molecular theory. It's basically all these molecules have this average speed, which is related to their average kinetic energy, and that average kinetic energy changes for temperature. And so this is how we get to the energy associated with thermal heat or thermal energy. Okay, go team. We have this relationship now. But I know what my delta E is. So this is equal to 1 minus, where's delta E? Oh, it's not up here. It was on the other board. Gamma H bar B0 divided by KBT. Okay, so this was from just a few minutes ago. All right, I'm gonna pause and erase. Okay, I rewrote it a little bit for you. So we've got the delta E, the change in the energy states upon degeneracy lifting in the presence of a magnetic field. The difference in those energies related to the Larmor frequency. This is the frequency that will cause resonance between these two states. Those populations are going to play a role in the intensity of absorption of the radio frequency that will cause the resonance. You've got in beta to in alpha, Taylor series expansion, assuming delta E is much, much less than KT. This is looking at the energy difference between E beta minus E alpha. So that energy difference has to be small, which is very nice that it's so small. And so if we want to look at the difference in the population between states, again, because the intensity, remember, was proportional to in beta minus in alpha. So, or sorry, in alpha minus in beta. So we know that in alpha minus in beta is also equal to in alpha times 1 minus in beta over in alpha. Check that out. Isn't that a fun little math trick? So I basically factored out an in alpha from this quantity. And so my in alpha times 1 is in alpha minus in alpha times in beta over in alpha just gives me in beta. But check that out. I've got in beta over in alpha ratio. I've got that ratio in terms of my delta E. So now I can say that this is approximately equal to gamma H bar B0 in alpha per KT. Sweet. Cool. So that's my proportion difference between these two states. And now I can also say, so assume that N is total spins, not net spin. That's different. This is the total number of spins, as in the total number of nuclei that I have. And that's approximately equal to 1 or twice in alpha. Again, it's almost 50-50, not quite, but it's enough that we can assume that it's 50-50. And so we're going to then say that in alpha is equal to N over 2. Again, that's the total number of spins that we have. If I make that approximation, stick that in there, and my intensity of absorption is equal to N alpha minus N beta times B0. I wrote this on the board a couple minutes ago. If I plug that into here with that reduced approximation and including the N over 2, I get that the intensity is related to gamma H bar N divided by 2 KT B0 squared. Okay, pause me, write all that down. I want to talk about it now. You know that we have a big ass magnet downstairs at Lawrence. The magnet is so huge in comparison to, like, what was it, 5 millitesla is the refrigerator magnet, and ours is like 12 Tesla. That's huge. So we have to have a really large magnet in order to split these states enough that we can see them, i.e. through the resonance, but also that we can have a high intensity of absorption. The other thing that's nice, as the temperature goes down, the intensity goes up. As your number of nuclei increases, your intensity goes up. As your gyromagnetic ratio becomes larger, your intensity goes up. So hydrogen has a diamagnetic ratio of about 26.7 compared to carbon-13, which is 6, compared to nitrogen-14, which is 1. We're about 2. So proton is like the most intense spectra that you can get in NMR because of this relationship of the Larmor frequency to the difference in the populations of the spin states. Go team. That's all I got for now on this. And now I'm going to jump to the next video, which is how do we detect things? Go team. Welcome to NMR. It's a beautifully elusive technique.